Chapter 6, Section 2, Solving Systems Using Substitution. Remember substitution. Substitution is when you plug in or substitute a value for a variable. Now, when we're substituting, it doesn't have to be like only entering 5 for x. If you had something that said x equals 3y plus 4, you could plug in the whole thing, 3y plus 4, in for x into another equation. So plugging in or substituting, it doesn't just have to be a number. It can also be an expression that you're plugging in. To use substitution with systems, you're going to solve for one of the variables in one of the equations and then substitute that into the other equation. Something that I'm going to say right now is that you have to show your work. There's no exception. You have to show your work when you're solving systems by substitution, as well as we talked about graphing yesterday, and we'll keep talking about substitution and another method. You have to show your work and you have to stay organized. If you don't stay organized, then you can do a whole bunch of work, and if you can't find different pieces that you need at different points, it's going to be really frustrating for you, and it's going to take you longer than it's necessary. You want to use substitution when one of the equations is already solved for a variable, or it is really easy to solve for a variable in one of the equations. If both equations are solved for a variable, just choose one of them to substitute into the other equation. Let's just go ahead and do an example of this, because we can talk about it a lot, but I think examples are what you really need to understand substitution. This example says, what is the solution to the system? Use substitution. Remember, a system of equations, we're trying to find one ordered pair that makes both of these equations true. Notice that they've given us y equals 5x, and then they've given us x plus y equals 12. To use substitution, we need to get a variable isolated by itself, which means alone on one side of an equal sign by itself. It doesn't matter which variable, and it doesn't matter in which equation. So if you look at these two equations, notice that y is already isolated in the equation y equals 5x. So what I can do, because this equation is already solved for y, is I can take the 5x, because y is equal to 5x, so I can take the 5x and I can plug it in or substitute 5x for y into the other equation. Notice I had to use the other equation. What that means, or what that tells us, is we can plug in 5x instead of y, and that gives us x plus 5x equals 12. So all I've done is I've substituted in 5x instead of y into the second equation. Well, x plus 5x, I can combine my like terms. X plus 5x is 6x, which equals 12. To solve for x, I need to divide by 6 on both sides, and when I do that, I get x equals 2. You might be thinking, well, that's super easy. X equals 2, we're done, right? Not so fast. Remember, the solution to a system of equations is an ordered pair. Right now, I don't have an ordered pair. I just have a value for x. Once I have a value for x, and it doesn't matter, you could also have a value for y at this point, depending on how you had to plug in. I need to take that x equals 2, and I need to choose one of the equations and plug in 2 for x to solve for y. It's going to be easiest to use the first equation, y equals 5x, to plug in 2 for x. So I have y equals 5 times 2. Well, 5 times 2 is 10, so y equals 10. Now I have an x value and a y value. I can create an ordered pair. Be careful here. Don't make a silly mistake. This is why being neat and clean and showing all of your work is going to be necessary. My x value is 2, my y value is 10, so I have an ordered pair 2, 10. Again, you might be thinking, oh, no big deal, that was easy, we're done. You are not done yet. You have to go ahead, just like we did when we were solving systems by graphing. I want you to go ahead and I want you to plug in the ordered pair, the x value 2, the y value 10, into both of the equations from the system to make sure that it is your solution. So to check your answer, just like we checked our answer when solving by graphing, we're going to plug in our ordered pair, our x and y values, into both equations to make sure that they are true. For the y equals 5x, I'm going to plug in 10 equals 5 times 2. Well, 5 times 2 is 10, so 10 equals 10. That is a true statement. That works for this equation. I'm not positive that this is my answer yet. I need to go ahead and plug in 2 and 10 for x plus y equals 12. When we do that, I have 2 plus 10 equals 12. Well, 2 plus 10 is 12, so again, that is an answer to this system of equations. Because this ordered pair, I found this ordered pair 2, 10, and because it makes each of the equations in the system true, I can say that 2, 10 is the solution to this system of equations. This next example says, what is the solution of the system? Use substitution. We're given 7x minus 3y equals 2, and then we're given negative 2y plus x equals negative 6. Neither one of these equations has a variable isolated already. Before I can substitute anything in, I need to have a variable alone by itself on one side or isolated. If you look at the equation 7x minus 3y equals 2, neither 7x or negative 3y is going to be easy to get by itself. We're going to have to either add or subtract and then divide to both sides of that equation. We would end up with fractions. It wouldn't be very pretty. It would work, but it wouldn't be very fun to get there. If you look at the equation negative 2y plus x equals negative 6, notice that x is by itself in the sense that it's not being multiplied by a number. So I just have the variable x not being multiplied, so that's going to take out a step. I'm not going to have to divide by anything, which means I'm not going to have any fractions. So I want to get x by itself in the second equation, negative 2y plus x equals negative 6. To get x by itself, or to solve for x, I need to get rid of negative 2y. Remember, I get rid of, this is like solving an equation for x. I have to use inverse operations. The opposite of a negative 2y is a positive 2y. So add 2y to both sides, and you get x equals negative 6 plus 2y. If you put 2y minus 6, that's going to be the same thing. Now, because x equals negative 6 plus 2y came from my second equation, I need to plug in negative 6 plus 2y in for x in the first equation. It always has to be the equation that that you didn't get the variable alone from. So because this x equals negative 6 plus 2y came from my second equation, I need to plug in negative 6 plus 2y in for x in the first equation, the other equation. When I do that, I get 7 times negative 6 plus 2y. Notice I've plugged it in parentheses because I need to distribute that 7. So make sure that you're plugging in the expression into parentheses so that you don't make a simple mistake. Minus 3y equals 2. Go ahead and distribute in your 7. 7 times negative 6 is negative 42. 7 times 2y is 14y. So you have negative 42 plus 14y equals negative 3y plus 2. Notice I have 14y and negative 3y on the same side. So I'm going to go ahead and do 14y minus 3y, which gives you 11y. So I have negative 42 plus 11y equals 2. I need to solve for y, so I'm going to add 42 to both sides, which gives me 11y equals 44. Now I need to divide both sides by 11, which gives me y equals 4. I have a y value. I need to find an x value. I can plug 4 in for y in either equation. It does not matter. I think, again, it's going to be easier to use the second equation because x is already alone. It's going to cut out a step that I have to do. So I'm going to plug in 4 for y. So I have negative 2 times 4 plus x equals negative 6. Negative 2 times 4 is negative 8 plus x equals negative 6. Now to get x by itself, I need to add 8 to both sides. And when I do that, I get x equals 2. I have an x value of 2. I have a y value of 4. I can combine those to make an ordered pair, 2, 4. Remember, I am not done solving a system of equations until I have checked my answer. So what I need to do in both equations, 7x minus 3y equals 2 and negative 2y plus x equals negative 6, I need to plug in 2 for x and 4 for y. The first equation, that would mean 7 times 2 minus 3 times 4 equals 2. We'll go ahead and multiply both of those. 7 times 2 is 14, minus 3 times 4 is 12 equals 2. Well, 14 minus 12 is 2, so that ordered pair does work for the first equation. Go ahead and check the second equation. You have negative 2 times 4 plus 2 equals negative 6. Negative 2 times 4 is negative 8. Negative 8 plus 2 is negative 6. So again, this does work because I have checked the ordered pair 2, 4 in both of the equations. 7x minus 3y equals 2 and negative 2y plus x equals negative 6. Because it worked for both of those equations, I can say that 2, 4 is the solution to the system. This next example says the school bookstore sells t-shirts for $8 and sweatshirts for $12. Last month, the bookstore sold 37 t-shirts and sweatshirts for a total of $376. How many t-shirts were sold? This is another systems word problem. So we know we have two pieces of information here. First of all, we know they're selling t-shirts and sweatshirts. Right now, before I even get started, because I have two different variables, t-shirts and sweatshirts, I'm going to go ahead and say we know two different totals, the total number of t-shirts and sweatshirts sold, and the total amount of money that was sold. What I was saying before is write one equation for each total, and I need to go ahead and say that x is going to be the number of t-shirts and y is going to be the number of sweatshirts. I'm going to go ahead and write that down so that I remember it after I've solved everything. So they tell us the price for sweatshirts, the price for t-shirts. They tell us how many t-shirts and sweatshirts total were sold, and they tell us the amount of money that was spent or sold of t-shirts and sweatshirts. The first equation that I can make is simply x plus y equals 37. However many t-shirts they sold plus however many sweatshirts they sold equals 37 because it tells us they sold 37 t-shirts and sweatshirts. The second equation that I can write is I can say that it's $8 for a t-shirt, $12 for a sweatshirt, and I know that they sold $376 worth. So I can say 8x plus 12y equals 376. It is important that your variables don't get mixed up here. Remember, x is t-shirts, and t-shirts are $8. Sweatshirts are y, and sweatshirts cost $12. So make sure that you're multiplying the correct variable by the correct number there. Now, to use substitution, which is what we're talking about today, I need to have one variable isolated. This first equation, x plus y equals 37, is going to be very easy to solve for a variable. I'm going to go ahead and I'm going to solve for x. So I'm going to subtract y from both sides, which gives me x equals 37 minus y. You could have absolutely subtracted x from both sides and gotten y equals 37 minus x. Either way, this should, if you follow all of the steps correctly, you should end up with the same numbers. I just simply chose to solve for x. There really was no reason to it. That's just what I did. Because x equals 37 minus y came from the first equation, I need to plug in 37 minus y for x into the second equation, so the other equation. What that's going to look like is 8 times 37 minus y, in parentheses again, make sure that you're putting those in parentheses, especially when it's an expression, plus 12y equals 376. Go ahead and distribute in your 8, multiply 37 times 8 and negative y times 8. So you get 296 minus 8y plus 12y equals 376. I notice I have two different y's. They're on the same side of the equation. I have negative 8y plus 12y, which will combine to give me 4y, a positive 4y. So I get 296 plus 4y equals 376. Subtract 296 from both sides, and you get 4y equals 80. Divide by 4 on both sides, and you get y equals 20. Now that I have solved for y, I need to go back to either equation and I need to solve for x. I don't really want to mess with that second equation right now because it's going to be so much easier to solve for x in the first equation. So always try to pick the one that's going to be easy on yourself. So when we plug in 20 for y, that's going to be x plus 20 equals 37. All I have to do to solve for x is to subtract 20 from both sides. When I do that, I get x equals 17. So to combine these, I would have the ordered pair 17, 20. I am not done yet. I need to go ahead and I need to check my solution in both of the equations that I started with. So go ahead and plug in 17 for x and 20 for y. When I do that, I have 8 times 17 plus 12 times 20 equals 376. Well, 8 times 17 is 136, and 12 times 20 is 240. 136 plus 240 is 376, so that ordered pair does work for that equation. The next equation is super duper easy. 17 plus 20 equals 37. 17 plus 20 is 37, so it does work for that equation as well. Because the ordered pair 17, 20 worked in both of the equations in the system, I can say, and I haven't actually answered my question yet, it says how many t-shirts were sold. This is where it comes in handy that I made myself that little note that says let x be number of t-shirts and let y be number of sweatshirts. Because I made myself that little note, I don't have to go back and try to figure it out. I've told myself already. So to answer the question how many t-shirts were sold, the answer is there were 17 t-shirts. I went ahead and threw in that there were also 20 sweatshirts sold. Infinite and no solutions when we're talking about systems. If when solving a system by substitution, you get an identity, like 2 equals 2, negative 9 equals negative 9, x equals x, then it has infinitely many solutions. So an infinite number of solutions. If when solving a system by substitution, you get a false statement. Some examples of false statements would be 2 equals 9. That's not true. 2 doesn't equal 9. X equals y is not necessarily true. And then negative 3 equals 3. Then the system has no solution. How many solutions does each system have? Notice for A, we have x equals negative 3y plus 4, and then we have 6y plus 2x equals 8. I already have an isolated variable, x equals the first equation. So I'm going to plug in negative 3y plus 4 in for x into this second equation, 6y plus 2x equals 8, Go ahead and plug it in. When you plug it in, remember parentheses, 6y plus 2 parentheses negative 3y plus 4 equals 8. Go ahead and distribute your 2, and you get 6y plus negative 6y plus 8 equals 8. When you go to combine your y's, you have 6y minus 6y. Well, 6y minus 6y is 0, so you're just left with 8 equals 8. This is an identity. It is a true statement because it's an identity and it's a true statement. I can say that A has an infinite number of solutions. So the system for letter A has infinite solutions because I ended with an identity. If you look at B, I have y equals 4x minus 9, and then y minus 4x equals 6. Y is already isolated in the first equation, so I'm going to go ahead and take 4x minus 9 and plug it in for y into the second equation, which would give me 4x minus 9 minus 4x equals 6. I don't have anything to distribute to the 4x and the negative 9, so they're just going to stay 4x and negative 9. When I go to combine 4x and then minus 4x, they cancel each other out, so I'm just left with negative 9 equals 6. Well, negative 9 equals 6 is not a true statement. It is a false statement, so I have no solution, or there is no solution to the system in part B.